Good day. This is the 7th in a series of videos designed to explain how to create predictive models which are simultaneously explicable and precise. This is the final video in this series, and we will take much of what we have done thus far and use it to create exactly what I said, a model which is simultaneously explicable and precise. And we will do this by introducing a set of functions that we will use to model the phenomenon in question. And then we will compare that to what came out of the xgboost and random forest modeling that we have already done in prior episodes. So first, let's introduce the new set of functions here. All right, so what we are going to discuss is a set of functions which are known as piecewise linear functions. We're going to talk about how to do modeling with that, what the strategy is going to be. We're going to show the execution of that in code, and then we're going to give the final comparison. So, what are we talking about when we talk about piecewise linear models or piecewise linear functions? Well, remember, always keep in mind what it is that we're trying to do. What we are trying to do, in most cases, in most predictive modeling cases, we are trying to estimate the conditional expectation. We know that it's a function of the variables that we are using to model. And so it's some function that is in Rn. It's defined on a subset in Rn, and for all intents and purposes, we can simply imagine that it is defined on the hypercube in Rn. And in fact, we have already previously transformed our variable so that that is the case. Recall that we use the integral transform, the probability integral transform, to take any sort of variable and make it as much as possible a uniform random variable. All right, so since we may as well presume that we have a continuous function on the hypercube, that opens up the door to questions like, well, what sort of functions or families of functions can approximate that larger set of continuous functions on the hypercube? And so there are many answers to this question. And in fact, one of the answers to this question are what are known as indicator functions, and that's what make trees work, and that's what makes, therefore, the xgboost models work and the random forest models work, is that both of those are tree models. Tree models are based on indicator functions, and indicator functions can, in fact, approximate any continuous function on the hypercube. But those aren't the only families of functions that can do that. Of course, one of the difficulties with those functions, random forest and xgboost, or rather those models, is that how do you interpret what's going on? And so while there are packages like Shape and stuff like that out there that basically take these models and attempt to answer that question, what we're going to do is bypass that complexity completely by starting with a family of functions which already have an easy interpretation, and that family of functions are the piecewise linear functions. So, what is a piecewise linear function? Well, it's a function that looks like this. Is that you're going to have, it's just a linear combination of stuff. What is the stuff? Well, there'll be linear terms, and there'll be terms that look like a transformation of your predictor variable. You take a look at max of your predictor variable minus some constant, and 0. And then take a linear combination of those guys. And that's a piecewise linear function. And so here's another one, a bit more complicated. We've added additional terms here. So now we have, 3 transformations of x, right? Is that we have just the straight up linear, it enters the function linearly, and then we have transformations of it all throughout. So these are examples of piecewise linear functions. Here's one that involves 2 different variables. So we've got x and y both entering the equation in a linear fashion here. Transformation of x, transformation of y, and now here is a product. So we are allowed to take products, but the product can only be to a single degree in either variable. So you can take the product of x and y, or you can take the product of the max of x minus something times the max of y minus something, but you can't have, say, x squared y, and you can't have, say, this factor in the term raised to a power other than 1. So you're allowed to take products, but they have to be only first degree. That's the thing. And again, that's one of the things that lends to the interpretability of these models, is that you don't have these crazy powers. You don't have polynomials to the 11th degree to model the phenomenon and then trying to make sense of what does the 11th degree mean? What is the interpretation of that in this case? Is that you have a much simpler set of functions here. So those are equations, right? But a picture is worth 1,000 words. How does this look in practice? And so we'll just take a very simple example. We'll take f of x equals x squared. And so how does that look? Well, that's just your classic parabola that you learn about the first time you take algebra, say. And it looks like this. And this is also the very first example you use to show the insufficiency of linear models. But what should be observed is that it's not so much the insufficiency of linear models. It's the insufficiency of linear models where you do not transform your variables. That's the key observation. Linear models are insufficient if you don't transform your variable. And so that's what you have here, is that when you regress against x, well, there's some up, some down, but when you regress against x, it all kind of evens out and you just get a constant function here. And so that, of course, is quite useless from a modeling standpoint, unless all you're after is the sample mean, in which case you wouldn't run a regression in the first place. So that's quite useless. Okay, so where do piecewise linear models come in? Well, we'll take a first pass at it, and we will consider a model, but now we will transform our variable x. We're not just going to let it enter in a purely linear fashion. We're going to transform it. And so not only do we have x here, not only do we have x here, but we also have a transformation. We have x minus 1, because we're looking at the interval -2 to 2. So obviously I just broke this interval up into two components, -2 to 0, 0 to 2, and I just took the midpoint, and I used that to create a value here, and then I regressed against these values, and what you get here is the green line here. So the green line is sort of a first pass using a piecewise linear function. So what do we observe here? Well, one is that obviously the green line does a much better job of following the parabola than the red line, which does no job whatsoever. And so the other thing, and this lends itself to the interpretability of it, is that not only does it do a good job, when I say models which are simultaneously explicable and precise, good job is the precise part of it, right? Is that the model follows the phenomenon. But the interpretability of it, explicable and precise, the interpretability is it's a connect the dots function, right? It's start here, go down here, take a turn across, take a turn up. It's really easy to explain what is going on in this model and what the implications are going to be on unseen data. You know exactly what's going to happen because the formula is so simple. And so now what you can do is you can have a more complicated piecewise linear function. So you got this guy here. And so what are we going to do here is that we just broke this thing up into, slightly finer components. So we're at, -4/3 here, -2/3 there, 2/3 and 4/3. And so now what do you see? Well, clearly when you use more terms, when you add more transformations of x, well, that allows you more flexibility in your model. And so it's obviously there's a corner here and a corner there, but there's also, you can kind of see one there, and of course it's symmetric, kind of see one there. You allow more flexibility in the model. The yellow line follows the parabola more closely than the green line. And yet, so it's got the precision part of it, and yet it's still explicable. It maintains its simplicity because the model itself is built off of simple things and just taking a linear combination. So again, it's connect the dots. Come down here, turn a little bit, come down, turn, turn, turn. There you go. It's connect the dots. So how does this look then, say, in 3-space? Well, let's take a look. So let's take something really curvy, okay? So we'll take a trigonometric function here, and here's what it looks like. So this right here is a trigonometric surface. It's a surface in 3-space, and here's the equation which governs it. So obviously quite curvy. Now, if you regress against just x and y, what do you get? Well, you just get a plane that slices through the trigonometric surface. This is very similar to with the parabola. You got a line that just cuts through it. The line does the best it can to kind of balance the the highs and the lows, but it's a primitive idea. And similarly, if you try to regress against just x and y on the trigonometric surface, well, what happens when you regress against x and y? You're going to get a constant plus something times x plus something times y. That's the equation of a plane, so it just slices through. It's flat. It does its best. You can see some of the, it's balancing the highs and the lows. Here's another view of it. Here are the lows. But, it's not really doing an awesome job, okay? So you do the same thing. You regress, instead of just against x and y, you also include additional transformations. So we're on 0 to 2 pi, and so that's why I'm just selecting pi to go into these transformations here. And so what do you have when you do this? Well, as you can see, you get something flexible, right? So now we're allowing bends in our modeling surface here. And that is how we are doing a better job of approximating it. So to get a sort of change the angle a little bit, this is sort of a flat face of it right here. Okay. And again, just like what we saw in the previous example with the parabola, if you add more terms, your approximating surface gets even better. So here's a bunch of other terms. Again, I'm just taking the midpoints, or just chopping up 0 to 2 pi and taking more points evenly spaced. And so now you get this yellow approximating surface here, and you can see that it's doing a much better job of approximating the trigonometric surface. And so again, what you have is you have a good approximation, so that's the precision in explicable precision, and yet the equation which governs the modeling surface here, the model surface here, are very straightforward. It's just these max functions here. And what you have is the two-dimensional version of connect the dots. And so graphically, this is a graphical argument. Obviously, it's not a full mathematical argument, but it's a graphical argument that piecewise linear functions can, in fact, approximate any continuous function to any degree of accuracy you like. So this is what's going on geometrically as you regress against more and more terms that look like this. So generally, what is a piecewise linear function? Well, it looks like this monstrosity here. So let's parse this equation so we can speak about it in precise terms. So keep in mind that when you normally do, say, linear regression against whatever, untransformed stuff, what does it look like? Well, it's the sum of coefficients times terms, right? So this whole big mess here would just be replaced with, your jth variable or something like that. But in this case, we've added additional complexity because we have this product here. And so what are we multiplying? Well, so what we have here for our model equation is it's m terms, m as in Mancy. And what is script p here? Well, that is the power set of 1 to n. So what we're saying is in each one of these terms here, of which there are m, in the jth term, we're grabbing a subset of our variables. Not all of it, maybe all of our variables, maybe it's just one variable. A subset of our variables. We're grabbing a subset of our variables, and then we are going to, this is the kth projection operator, so that just picks off your kth variable. And if we want a constant term, if we select the empty set from the set of our variables, we'll just say that's a constant term. What is b here? Well, that's just some vector in Rn. So we've got n variables, n as in Nancy, and we've got a vector of real numbers in Rn. And so we're going to take our kth variable, and we're going to take the kth number in that vector, and we're going to do something to them. That's what f is here. What are we going to do to them? Well, we have two choices here. We have two choices that come from our good friend, Mr. Friedman, from 1991, from his Mars paper. And either you're going to take the max of your variable minus the number in 0, or you're going to take the min of your variable minus the number in 0. And that's it. So this term here, or rather this factor here, this guy here, it's either a max function or it's a min function. It's one of the two. And so again, it's just not complicated. It's max, it's min, whatever. And then it's one of your variables, and then you subtract something and you take the max or min of that and 0, and then maybe you make a product of them. Okay, so that's what's going on. So that's how Friedman wrote his paper in 91. Now, what we're going to make is a few observations here, which are going to help us later on. So the first is that you might say max and min. Well, that's odd, Ian, because all throughout this presentation thus far, you've been using max functions the whole time. Why is that? And the answer is because your min functions can all be written as a linear term minus one of those max functions. And so, for all intents and purposes, instead of thinking in terms of mins and maxes, you can think in terms of linear terms, or if you will, untransformed terms, and max terms, like this. So we only have to consider one transformation, max, instead of two, max and min. So that's one reduction in complexity. The next reduction in complexity is to note that, well, if you have a term that looks like this, and k happens to be less than whatever variable in question it is you're discussing, that is to say, outside the range of what's in your data, well then, you can represent a linear term here as the max function. So, you don't even really need to think in terms of max and linear. You really just can think in terms of max. You got your max function transformations, and that's it. Or a constant, of course, because you need the constant. Okay, so the next thing is that, and again, this goes back to the fact that we talked about categorical variables and what to do with them, how to group them, and so that was the whole point of the increasing groups lecture. But here's the thing. If you have a variable that takes only two values, now I'm thinking in terms of 0 and 1, but really this applies all the time. If it takes only two values, K1 and K2, and you select a K bigger than either of those, then this transformation here just equals 0. So who cares? And moreover, if we just assume that you take a K less than K2, so here we've got K greater than or equal to K2, where K2 is bigger, then you just get something that's 0. But if you take a K less than K2, well then this max function just equals a linear function. It's just the variable entering linearly. And so for all intents and purposes then, if you have a categorical variable, you don't have to consider transformations of it. Just put it in there. Who cares about transformations? There are no useful transformations to make here, because when you make your max transformation, all you do is wind up with a linear plus a constant. So you might as well just have it enter in linearly. Okay, so with these simplifications in mind, what is our modeling strategy? And so we already have done part of this is, well, one, we group the categorical variables to reduce the number of variables under consideration. And so, again, this goes back to the increasing groups lecture. And the reason we do that is because for categorical variables with a large cardinality, say zip codes or something like that, there's just too bloody many of them, right? There's 32,000 zip codes, something like that. I mean, there's like 40,000, but there's a lot of like P.O. boxes and army bases and stuff, so who cares? It greatly reduces the number of variables and thus speeds up computation time. If you had a computer with infinite computational capacity that would run in seconds, you might be able to get away with something, but we don't. So, next is we're going to use the Mars routines to obtain a piecewise linear model. So I just gave an argument for why you would consider such models, piecewise linear models. And again, the answer is because they can pick up all signal. That is to say, they're precise. But the transformations are so simple, it's just connect the dots so that it's still explicable. And that's why we do that. The Mars routine, so Friedman in his 91 paper proposes this particular modeling technique. He implemented it in some proprietary software, but other people have read his paper and implemented it in open source, and we will be using the Earth package instead of Mars in the R code for this. And so what we're going to do is we are going to run a Mars routine, and that's going to give us an initial piecewise linear model. Now, because it's a Mars routine, it's going to have both min and max functions that it recommends. And so what we're going to do is we're going to convert all of those. We're going to convert all the mins into functions that have only linear and max factors in the terms. And then that's going to be our initial set of transformations to consider. And then what we're going to do is we're going to select from among those transformations using ever stringent criteria. So first, we're just going to stepwise select among them. And the other thing is that we are going to start with smaller degrees. So again, this goes back to the simplicity thing, which is that equations which have terms with only one factor are easier to explain than equations with terms with two factors, than equations with terms with three factors, and so on. So we want to start small and slowly build our way up in terms of complexity. And so we want most of the signal to come from the linear terms if possible. And then whatever comes out of that, we are going to cross-validate, which is a much more stringent selection process, but also computationally more expensive. And so that's why we don't cross-validate everything. We cross-validate stuff that is stepwise selected. And so that greatly reduces the number of terms in the equation. And then finally what we do is we then we actually have a model that we can examine for plausibility and explicability. And so again, the whole point of all of this code, all of these automatic routines is not to automatically build a model a la Data Robot or some other silly thing. The point of it is to quickly get you to an initial model that you can examine and make little tweaks on. But first you just want a fairly decent, precise description of what's going on, but done in a way that is still explicable. And so that's what we're doing there. And so without further ado then, let's go to our good friend, RStudio. All right, so what's going on here? Well, like I said, we are going to run some Mars models. So we have to say how complex these Mars models can be. So remember, in the terms, in the equation for a Mars model, you have terms where it's either linear or it's a max function. And then you have products of those things, products of two at a time, 3 at a time, 4 at a time, 5 at a time. So obviously when you take x times y times z times w times a, it's kind of difficult to explain. So you don't start there. You start with just terms with one factor and then build up to 2, 3, 4, and so on. And so we're going to let the maximum investigation degree, I'm just setting it at 5, and we'll see what actually comes out of it. So let's load everything up here. Again, these data sets are the data sets that you've seen previously. Nothing crazy going on there. And now we're going to run this loop here. So I want to explain what's going on in this loop. So here is the Earth formula. And so what have we done? We've thrown in every variable that we've created so far. So the variables here consist of the continuous variables that we hit with the probability integral transform. And then it consists of the indicator variables for the groups that we created with the increasing groups function. And all of those guys are contained in this design matrix here, design matrix 2. So here's all of your variables, as you can see, with all these zeros and ones. These are just the indicator variables, all of these messy floats here. These are your probability integral transform variables. And of course the missing indicators as well. So that's what's going on. And so what we're saying to the Earth function, which runs the Mars routine, we're saying, hey, here's your data set, here's your target. Just start going through, take a look at each variable, perform some transformations and see what happens, see what comes out of it. So we're going to let that run while I talk through the rest of this. So what's happening here? Well, we know that the maximum investigation degree we already said was 5, so we're considering models that have terms containing up to 5 factors. And what we're doing is, as this loop goes, we're allowing more and more complex models. So when I equals 1, it's only considering formulae whose terms have 1 factor in them. It's done. When I equals 2, now we're allowing terms with a product of 2 factors, and so on. We're allowing it. It doesn't have to select a term with 2 factors, but we're allowing it, and we're just sort of like seeing at what point we start to not need it, those higher degree terms here. And so that's what's coming out here. So this is the model output. We'll just take a look at that real briefly. So a bunch of stuff, and that's of course the print command. The model output is in fact a list, and so the point of the model information here, the format Earth output function, is it takes the model output from the Earth routine, and it just parses it. It does exactly what we said we wanted it to do, which is that we're going to transform our minimum functions into linear minus a max, and so on. And so we're actually going to disentangle all that stuff, and that's what's going on there. So model information is another list object. It looks like this. So this is what comes out of, say, the Mars routine, the Earth routine that runs the Mars algorithm. This is the straight stuff. And then what exists here is the translation of all this raw stuff from the Earth routine into more information here. Okay. And then here, this is just checking in the loop whether or not we need to consider higher degrees. So that's that. Now, it should be understood when you're using this stuff to make sure that you understand how things are being calculated. And so the model output gives you a goodness of fit. So it's saying the R squared on it. On the training data was the 0.95. Can we reconstruct that with just model output? And the answer is yes. And that's the point of this equation here. So we can do that as well. Recreate the fitted values. So basically this confirms to us, that comes in, it might as well be 0. So what's that saying? Well, what it's saying is part of the model output is it actually creates the design matrix of the terms it created and selected. And so when you multiply that with the coefficients that are in it, so this is just, take a look at this. So those are the terms it created. H stands for hinge, the way Friedman thought about these functions. He thought of them as hinge functions. And the reason why is because if you graph max x and 0, it goes whoop, whoop, like that, or min. Whoop, whoop. He thought of that as a hinge. So H for hinge. that's why that's in there. All right, and then it gives you the coefficients on the terms. So like that. And then if you take that linear combination, you get the fitted values. And so what that's telling you then is that what this is doing is it's minimizing sum of squared errors. That's one of the things we learn from here, from the R squared. It's minimizing the sum of squared errors, and also it's not transforming the linear combination. It's just the linear combination. There you go. And so we are going to create that on the whole of the design matrix. So in here, like good little data scientists, we restricted our attention to just the training data, but now we want it on the full data set. And we'll make sure that we didn't screw it up somehow. Nope. Okay, good. So we did that correctly. And now, because we have the same sort order on the standardized data as opposed to the design matrix, we're going to just create it on the standardized data by making vectors equal to each other. And lo and behold, our sum of squared errors is equal, so that shows that the sort order was in fact correct and we didn't screw something up. Okay, so here we go. Now, just for our own edification here, what we're going to do is just get a sense of what was going on. So, model information, that's what came out of the Earth routine. Just the raw stuff untransformed. And what we saw, what this is telling us is that there were 49 terms in that model. 22 of them were just straight linear, not linear, but one-factor terms. 22 of them were terms that had 2 factors in them, and we actually had 5 terms which had 3 factors in them. Okay, but when you disentangle all of that stuff, and by disentangle I mean when you rewrite your mins as linear minus a max and create the implied terms that come from that, you pick up a lot more terms. So now we're up to 47 terms with the factor 1 factor in it, 45 terms with 2 factors in it, and 6 terms with 3 factors in it. Okay, and so what this is going to do then is create term function here, just to give you a sense of it. So if we, for instance, let I equal 1, what it's going to do is it's going to pick out the ith term. And so in the ith term, apparently 2 variables appear. So they're the ith term, or the first term, is a product of 2 functions. These are the variables. And then we go and see what the knots are. And so the knot on one of them, that the minus k part of it, the k is 0.91. And there is no transformation of the other one. It's just going in linearly. That's what that means. And so then what happens is that we are going to, there we go. We are going to create that term here. Most of them are 0, but some of them are non-zero. And that's the point of this function here, is it's going to go through the expanded model table here, all 98 terms of it, and term by term, it's going to say, okay, well, what were the variables? Okay, what were the knots? The thing that you subtract off. Okay, now take the product of them. All right. And the reason we have to do this is because although the Earth routine lovingly gave us the design matrix, it did not give us the design matrix for what happens when you disentangle the minimum terms and write them as a linear minus a max. And so we have to create that manually, and that's the point of this right here. So we are going to create all of those terms like that. That's in design matrix 3 here, which has 98 columns, as it should, because there were 98 terms indicated in the table. And we are now going to compare this to the columns in the Mars matrix. So again, what happens is that the Mars matrix, or the design matrix that came from the Earth routine, some of those terms contain min functions and some of them don't. So for the ones that don't, the terms we just created, we should be able to find columns in there, in the design matrix that came out of the Earth routine. We should be able to find a column in there that matches one of the columns we just created, hence the function column compare. And so that's the point of the column compare function, is it's just a double check of our work. It's going through and it's making sure that where possible, the columns that we just created match what comes out of the design matrix in the Earth subroutine. And lo and behold, we agree that the number of columns in the design matrix that comes out of the that comes out of the Earth routine matches the number of columns that appear to have a match. And then we go through and look and just see. And lo and behold, yep. So what this is doing is it's going through and it's comparing what's in the design matrix coming from the Earth routine versus what we have here. And so, yeah, for instance, we can look at, say, this guy here. So what do we see? We see, well, okay, it's a max function minus this 9.6 whatever. And lo and behold, that's exactly how we used it as well. we had a term that had a 9.6 in it. Here's a term with two factors in it. Variable 13, variable 23. And these were the knots they used, 0.87, 0.84. And lo and behold, those are the knots that we used. So, therefore, where we can match the design matrix that comes out of the Mars routine, we do match the design matrix that comes out of the Mars routine. So, hey, good for us. Okay. So now that we have that, we are going to create a model with all of the terms we just created. So keep in mind that the Mars routine gave us 49 terms. We have 98 terms, I think. Once we rewrite our mins as linear minus max. And so we've got more terms, so therefore it should be more flexible, and lo and behold, that's what you see in the correlation here, is that the correlation is 0.977 on the training data for just the raw model that came out of the Earth routine, and then for us, we've got a slightly higher correlation, but that's to be expected because we have more terms, and those terms encompass the terms that came out of the Earth subroutine. Now, it should be observed that it's not much more correlation, so you might reasonably say, why is that? And the answer is, well, because at this point, we have absolutely overfit what's going on in this phenomenon. Mars gave us 49, which was probably already too many, and then we made 98 out of it, so we've got way too much stuff in there, okay? So that's fine. Because the idea is to first get a very simple, fast model, and now we're going to start paring it down. So the first thing to do is to bring in the original data set here and to get our list of continuous variables, okay? So the selected continuous variables, what is this? Well, this is coming from our expanded model table. And it's all of our continuous variables. So recall at the beginning of this, what we did was we had all sorts of variables and they were on all sorts of scales, and then we hit all of them with the probability integral transform, which transformed all of those variables and all those scales into uniform random variables. And all this is saying here is that, in these different terms, you've got, say here in term 4, you've got some variables transformed into variable 13, I don't know what, and we used a knot of 0.84, and some other variable was transformed into variable 23, where we used a knot of 0.87. Okay, so now what we're going to do is we are going to, now that we have a model now, and it's explicable and precise, but what we're going to do is we're going to undo all of the work we originally did. So originally, again, remember, you're given this raw data set. It's got missing values. It's got categorical variables. It's got continuous variables. The continuous variables of all sorts of scales. And what we did was we said, I don't want to deal with that complexity right now. Transform everything, make it all uniform. But now that we have a model, what we're going to do is we are going to transform it back. We're going to take the information that comes out of this model, because what this model is saying is, hey, the behavior changes for variable 9 at 0.91, whatever variable 9 is. And so what we're going to do is we are going to say, okay, well, what is variable 9? And to what does 0.91 translate for variable 9? And that is the point of this next piece here, the not translation. So we're going to going to initiate this. So again, we'll just use I equals 1. Then we'll go in and we'll say, okay, well, what is the first variable that we see? Okay, well, it's variable O2. All right, so what we do is we go into our translation table. This is the translation table created in the very first piece of code where we took all of our continuous variables, hit them with the probability integral transform. So this is what allows us to connect the original data with the transformed data, which gives rise to the comment that I make so often, which is that the hardest part of data science is the bookkeeping. But if you do your bookkeeping in a rigorous and algorithmic fashion, it's not terrible, but you have to do it. So anyway, so what we're going to do is we're going to go into this translation table. We're going to find variable O2, and we're going to see to what it corresponds. And apparently it corresponds to lot area, the size of the lot on which the house is sitting. And then we're going to get the knots, the minus k part of it, that appear. So we've got NA and 0.98. So, okay, good. So get our knots, and of course NA means that the term just enters in linearly, right? So we're going to check to see if one of the knots is in fact NA, which it is. Okay, so now we've updated the knot translation table. And so what you can see here is exactly what I was saying is, here's the transformed variable, here's the knot. What is this variable? It's lot area. So what is the meaning of the knot? Well, this entered in linearly, so this should enter in linearly. All right. And now we've removed the NA knot. We're going to see if any more remain, which indeed they do. And so now what we're going to do is we are going to run this little for loop. And it's going to go through, and what it's going to do is it's going to translate the transformed variable value into an original variable value. So variable O2 was just some uniform random variable, and we said, things start to change at 0.981. And so you go, what's the meaning of that? The answer is, well, the variable was lot area, and what corresponds to a value of 0.918 is the value 25,419. And so what this is saying then is, from this sort of abstract model, we have translated it back into concrete terms. And what we're saying is, apparently, the value of the home price, its relationship with lot area changes when the lot size exceeds 25,419 feet, I suppose. I haven't looked at the original value of the units, the original units of the lot area. Okay. So here we go. All right. So that runs. Okay. And now this is what this thing looks like in totality, right? Is that you've got different variables here. So here's, say, garage year built. So apparently the year in which the garage was built has some effect on things. Who knew? Not I. And so in the first case, it just enters in linearly. So apparently there's some effect there. Apparently that changes on the transformed variable at 0.362. Well, to what does that correspond in real life? 1969. And changes again on the transformed variable, coming from the Earth routine, at 0.961. What does that mean in the real data? The year 2007. So now we've taken our Mars model, and we have now taken the continuous variables, and we've translated them back into their original variables and into their original values. And now we're just going to make sure that our row counts check out. And good, they do. Okay. And so now what we want to do is, now that we have translated what the Mars model was telling us, we are now going to create a model using the original variables, the ones that the stakeholder actually cares about, because the stakeholder doesn't care about probability integral transforms. Like, you can't go to a stakeholder and say, "Oh, by the way, I took the square footage of the house and I hit it with a probability integral transform, and things really start to heat up around 0.42. They don't care. They want you to make recommendations in terms of the actual square footage. And so the Mars model gave us the meaningful where the meaningful changes take place. We are simply translating that back into the original data. And we are also going to include the categorical variables there. So that's what's going on there. And now the expanded model information, the original one was done in terms of the transform variables. This one is going to give us that information in terms of the original variables here. Transform variable, not. Original variable, not. Okay. And now, just as before, so again, we'll let I equal 1. Just as before, when we were creating the terms using the transform variables, we had the create term function. Now we're going to redefine the create term function to create terms, not in terms of the transform variables, but in terms of the original variables. So now this is going to go through and it's going to say, okay, well, who's in term 1? And the answer is no longer some abstract stuff. We still have a categorical variable in here, 1196, but the continuous one has been translated. Total basement square footage. So now we have like meaningful stuff. And you might say, well, value 6 for variable 119 is not that easily understood. It's like, yeah, but it's easily translated. Because this is just a collection of whatever went into variable 119. So if you go to translation table, variable, and you look up variable 119 in here, well, actually, it's going to be, it's not going to be in here. It's going to be in, it's in translation table 3. Yeah, so 119 corresponds to 45, and 45 corresponds to neighborhood. So that's what's going on there. So this is just right here, this is just saying some collection of neighborhoods multiplied by the total square footage of the basement. That's what's going on there. Then you get your knots, just like before, except now we're doing it on the raw data instead of the transform data. And so, of course, there is no knot for a categorical variable. And this is saying that apparently the transformation is max total square footage of the basement minus 1,626. So what this is saying is that whatever effect the square footage of the basement has on the price of the house, that effect changes after 1,626 square feet. And then we just create that term. But most of it's 0. Here's a 72. Here's an 11. Ooh. 1512 plus 1,600. 3,000 square foot basement. That's a big basement. Okay, anyway. So, the create term function. And so what is design matrix 4? Design matrix 4 then is Mars gave us knots on our transform variables. We translated those knots. Now we've created piecewise linear functions using the raw variables. So now we're going backwards so that we can get, like I said, an explicable model, a model in terms of the raw variables, a model in terms of year built, a model in terms of square footage, not a model in terms of variable 37. We just figure out what value we should use for our missing value placement, and apply it. Nothing crazy there. And we include our missing indicators because we have to account for the cases where continuous variables are missing. Okay. So now this is finally what our model information looks like. here's the term, here are the variables involved, here are the knots, and so on. Okay, and I threw in the degree there. Why did I throw in the degree? In a certain sense, it's redundant. It can be deduced from the table. It's because what I want to do now is I am going to first create a model where I'm only going to look at terms that have one factor, that is to say degree 1. Why am I doing that? Again, because I want to build the complexity of my model upward. I don't want to start with a complex model if I can get away with a simpler one. So I'm going to start with a simple model, and then we're going to build up from that. So here we go. And now we're going to stepwise select, and that's the step AIC function. The step AIC function is a great function. It's in the mass package. It runs, as you can see, fairly quickly. Great function. However, if your data sets are large, you might want to consider, because of course stepwise selection is just running a loop, you might want to parallelize it. I contacted the authors of it, and one of them got back to me. He was really nice. I said to him, "Hey, are you guys ever gonna? You guys built a great function here. Are you ever going to, parallelize it now that we have this capability?" And he informed me that both he and the other fellow who authored it are long retired. They said no. And so I created a stepwise function, which is parallelizable. It's on the GitHub. I didn't use it here, but it is available for larger data sets. It greatly speeds things up. Okay. So what do we have? So now we have a main effect model here. And so again, this is a model where we were only looking at terms which had a single factor in them. And so let's just get a sense of how good this is, right? So, okay, 0.9475. And so this is not a mathematical statement. This is an empirical statement, but a lot of times when you're doing this work, most of the power in your model is going to come from linear terms. Just don't get too clever. Just apply your transformations, take a linear combination of them, and that's where most of your power is going to come from, and that's what we see here. Is this the same correlation as the Mars model? Of course not. No, that was coming in, 0.97 or something like that? But that's a much more complicated model. And so here we see that much of your power is coming in from your main effects. Okay, so we are going to create an offset using that. So we're going to fix the main effect portion of the model. And we are going to mark the terms that have been selected thus far. So included the selected column here. And so that's that. And so now what we're going to do is, now that we have a model of terms which contain one factor, now we're going to begrudgingly say, okay, we'll allow a little bit more complexity. Now we're going to create a formula where these are all of the terms that have two factors in them. So they're more complicated in terms of their explanation, but hey, we'll see what comes out of it, all right? And so we are going to create the second order model using the first order model as an offset. Now, technically, what we should do if we wanted to be really good data scientists is we would stepwise select from all of the terms instead of fixing the linear part of it. But the reason I don't is because, again, you're trying to save on computation, and you're also trying to only select second order terms to the extent that they improve upon the first order terms. You want to favor lower order terms as opposed to higher order terms if you're worried about explication here. So we'll run step AIC again, except this time it's running on second order terms. So look at it go. And recall the value of the correlation that we got out of it last time it came in. Something like 0.94 or something like that. And so what you'll see when we run this now, the correlation goes up. It went from 0.94 to 0.97. So it goes up, right? But but it went up by 0.03. So the lion's share came from the main effect, and we are just lily gilding at this point. So now we're going to create an offset from that. We're going to update our table, and then we're going to create a model where we select among, these are the terms that have 3 factors in them. So we're allowing even more complication. So here we go. Run that. All right, well, that's done. And okay, so I guess we got a little bit maybe at the 3rd decimal point in terms of correlation here, but we're really running out of signal, right? Okay. So now we've got all of our selected terms. And so now what we're going to do is, now that we've selected our linear terms, we've selected our 2nd order terms, we've selected our 3rd order terms, what we're going to do now is we are going to cross-validate all of them. And so let me kick this off and just make sure that we're going to kick this guy off, and then I'm going to explain what's going on inside. So, So among other things, the GLM cross-validation here does take a cluster as its argument. This thing is parallelized cluster of 8. Not on this computer. It did the work originally on a bigger machine. We'll just do a cluster of 4 here. So we'll make a cluster of 4. And now we'll let this loop go. And away it goes. All right. So what's going on inside this loop here? Well, what we're doing is we are running rounds of cross-validation. So cross-validation here, what this is doing is it's just doing a round of it. And it's splitting the data into 70, so 0.7, splitting into 70, 30. How many times is it doing it? It's doing it 10 times. And now what it's going to do is it's going to build a model here, and then it's going to, it's going to apply the model on unseen data. It's going to record the error, and then that's going to be that. And then it's going to do that, like I said, 10 times. And then you can see for any given variable, if it's already in the model, what happens when you subtract it. If it's not in the model, what happens when you add it. And then you're going to see, okay, well, is it worth including? Is it worth excluding? Am I overfitting it? You know, that kind of thing. Okay, and so that's what's going on with the error table here and, you know, all this stuff. So what's going on is that if we go and look at our good friend, Mr. Excel, I already have, in fact, the output from this, because I run this previously. This is what the output from this thing looks like, a single round of this. So a single round of this produces one error table and one parameter estimate table. And so what you're doing with the error table here is you are saying, okay, well, let's just take a look at, say, you know, variable v1, term 1. What happens? Well, what happens when we include term 1 and then we create a model over here and then apply it over there? What happens is we get these different measurements of error coming out of it. We get an average error of, looks like 79,586. Okay. And then we're going to do that again for term 2, Mr. V2 here. There we go. And when we do that, what do we get? We get an average error of, when we include it, we get an average error of 113,054. So that's way worse than term 1. So we're probably not picking V2 here. Certainly not over V1. All right. And then we're just doing this with every variable here. And so now, which one was picked? Well, if you go and look in the second round, you know what was picked because it's now included. Apparently, variable V45 was picked. So in here, V45, V for vendetta, V45, when you look at it, what's the average error? It's 58,266. But when you look at, so that's 45, 58,000. When you look at just the base model, the starting model, the average error is 79,000. So great reduction in error. Wow, that's great. Now, but there's one other thing that we want to keep in mind is that one, and this is just sort of shows my inherent conservatism. You can, of course, adjust this however you like. But one of the things to keep in mind is that I personally want consistent error reduction. So I don't want it to be the case that, hey, sometimes including V45 is good, but sometimes it's, seems to make things worse. No. I want consistent error reduction when I include V45. So that's one thing I want. But there's something else I want, and that's why we include this table of parameter estimates in here. And so again, if we go and take a look at the ones involving V45, here we go. And get rid of the intercept terms. Don't care. All right, so what do we see here? These are the parameter estimates on V45. And what do you notice? Well, one, they're all positive, okay? What does that mean? It means it's always pointing in the same direction. It's always the case that we're saying house price goes up as V45 goes up. It's not saying house price, so if one of these things was negative or a couple were negative and a couple were positive, then what it would say is, hey, sometimes the house price goes up, sometimes it goes down. Again, in terms of explicability, that's terrible. What are you gonna say to the stakeholder? What happens when the square footage goes up? Well, it's kind of hard to say. Sometimes it goes up, sometimes it goes down. It's really anyone's guess. Okay, no, we're not doing that. What we want are consistent signs on our estimates. We want them all positive or we want them all negative. Again, you don't have to do this. You can change the program however you like, but it shows my inherent conservatism. And the other thing is that look how nicely these estimates here are. The average value here is 3.389. They're all kind of in that general vicinity, right? None of these estimates here is this is a 0.37 and this is a 14 and this is a 2 million or something like that. No, they're all roughly in the same ballpark, right? And so again, what that shows you is stability of your parameter estimates. You want your parameter estimates always pointing in the same direction. You want them to look relatively stable. And you want consistent increase in the precision of the model. That is to say, consistent decrease in the error. And so this file here is what happens when you run all that R code. So let's go back to our good friend RStudio. It appears that it is still running. Oh, hey, it just got done. Yes. Okay, cool. So all of that's incorporated in here. The error table construction. Sign check is doing exactly what you think it's doing. It's checking to see how often stuff is positive or negative, and that it's selecting the chosen term. It's selecting the variable according to the criteria that I laid out. Again, if you want to adjust some of this stuff, you can, but I don't. All right, so all well and good. So we've got our results now. So now we'll turn off our cluster so we don't blow up the computer. Yep, okay. Cluster's turned off, so that's good. All right, but now we come to the finale here, right? Again, the whole point of this, the whole point of all of this stuff is to create models which are simultaneously explicable and precise. And so early on, to help us with our grouping, we did create, I'm not saying xgboost doesn't have its place, I'm not saying random forest doesn't have its place, I'm not saying neural nets don't have their place. They all have their place. And we used them early on to quickly create precise models. They just weren't explicable. We still used them. And so now the question is, how do those models perform against what we just created? So we're going to bring them in. We now have a piecewise linear model, that is to say an explicable model. We have an explicable model on our data set in terms of our original variables. So we have an explicable model. And we also have these machine learning models. We've got an XGBoost model. We've got a random forest model. So let's see what happens. Okay. So first we're going to look and see what happens on the testing or the training data. We'll look at the correlation between the models and the housing price. So, all right, XGBoost, correlation's coming in at 0.96. Random forest correlation's coming in at 0.98. Okay. And in last place, oh no, in last place, this whole video series has been a lie. In last place is the piecewise linear model coming in at 0.95. But here's the thing, is that on the training data, well, it's the training data. You can hug that data. Your model can hug that data as precisely as you wanted to. Just throw in more terms, right? I didn't have to cross-validate my terms. I could have used. You'll recall. I think we started off with 0.97 or something like that after the third order model, which would have beaten the random forest and come close. Or I'm sorry, would have beaten the XGBoost and come close to the random forest model. I could have just thrown in more terms, and I would have gotten my correlation up. The real test is what happens on the testing data. And lo and behold, the XGBoost model hugged the training data too tightly. The correlation on the testing data is only 0.93. Same thing for the random forest. Correlation on the testing data is 0.93. But the piecewise linear model on the testing data is 0.94. So in fact, it beats the XGBoost model. It beats the random forest model. You in fact can have an explicable model which matches the precision of machine learning models like XGBoost and random forest. And this is a demonstration of that. Hope you found this presentation to be useful. If you have any questions, please leave them in the comments.